The following video is on continuity. When you were in high school, you probably learned the definition of continuity is any graph that you can draw without picking up your pen or pencil. Unfortunately, this definition only makes sense if we know about the graph of the function. Many times, we'll be handed a function that we don't want to have to graph, and we'd like to decide whether or not it is still continuous. In this lesson, we will learn the formal definition of continuity. Consider the following four graphs. The first graph, f of x, has a hole at a comma b, and you'll probably recognize that this function is not continuous at x equals a. Notice that f of a does not exist, and the limit as x goes to a of f of x equals b. We'll talk about why that is important in a minute. For the second graph, we still have a hole at a comma b, but notice that that hole is filled by a solid dot at the point a comma c. So in this example, f of a equals c, and the limit as x goes to a of f of x equals b. In this third example, notice that we have a solid dot at a comma b, but then our function jumps down to a comma c for all values of x greater than a. So in this example, f of a equals b, but the limit as x goes to a of f of x does not exist. In our fourth example, we have a function that has a solid dot at a comma b. Notice that in this example, f of a equals b, and the limit as x goes to a of f of x equals b. And out of all the examples that we've looked at, this is the only one that is continuous. So let's use this notion of the limits and the value of the function at the point to define a formal definition of continuity. We'll say that a function f is continuous at a point x equals a if and only if the following happen. F of a is defined, the limit as x goes to a of f of x is defined, and the limit as x goes to a of f of x equals f of a. If all three of these things happen, we'll say that f is continuous at x equals a. So here we're going to rewrite the definition, and let's try the following example. Let's look at f of x equals x squared minus x plus 2 divided by x minus 3. This function is not continuous at x equals 3 because f of 3 does not exist, which remember is the first condition of continuity. Looking at another example, let's look at f of x equals x over 2 if x is not equal to 1, and 1 if x is equal to 1. This function is not continuous at x equals 1 because the limit as x goes to 1 of f of x is 1/2. Remember, with limits, we don't care what happens at the point x equals 1, just what happens close to it, so we're going to use the function x over 2. But f of 1 equals 1, so notice that we've failed the third condition for continuity, that the limit as x goes to a of f of x needs to equal f of a. Once again, I've written our definition. Let's look at the following example. F of x equals x over 2 if x is not equal to 0, and 0 if x is equal to 0. This function is continuous at x equals 0 because f of 0 equals 0, the limit as x goes to 0 of f of x equals 0, so both f of a and the limit as x goes to a exist, and they're equal. So how do we test a function for continuity? First, find points you are worried about. These usually consist of points that are not in the domain of the function, such as points when you would need to divide by 0. You also need to look for points where two or more pieces of a piecewise function are being glued up. Then you're going to take all these values and check them using the definition for continuity. Let's look at an example of this. So let f of x equal x squared minus 1 over x plus 1 if x is greater than 0, 2 if x is equal to 0, and x squared plus 1 if x is less than 0. We are worried about x equals negative 1 because we might need to divide by 0. We're also worried about x equals 0 because this is a value where we're gluing up multiple piecewise functions. Notice, however, that we don't need to worry about x equals negative 1 because when I check it against the definition, f of negative 1 equals 2, and the limit as x goes to negative 1 is also 2. Looking at the same problem from before, let's now check x equals 0. F is not continuous at x equals 0 because the limit as x goes to 0 from below of f of x is 1, but the limit as x goes to 0 from above of f of x is negative 1, and these two values do not match up. So notice that the limit does not exist at 0. This is one of the requirements, however, for the function to be continuous. So notice that f is continuous everywhere except at x equals 0. Alright, so to summarize what we've learned in this video, in order for a function to be continuous at a point x equals a, f of a must exist, the limit as x goes to a of f of x must exist, and these two values must be equal. To check for discontinuity, first find the values not in the domain of the function, or values where we're gluing up several piecewise functions. Then, test each of these points that we're worried about against the definition for continuity, which is listed above.